All right, it's 4 o'clock, so let's go ahead and get started. All right, good evening, everyone. How's everyone doing today?
Doing all right, Dr. Trent.
Good to hear it. Exhausted, yeah, I know. It's been 2 weeks, but it's I wish it was summer already. Probably you guys all feel the same way. Okay, so it's the end of week 2, and so we have one more lecture today, and so I'm going to go ahead and continue basically where we left off on Tuesday, which is doing a little bit of fluids review, but today we're actually going to see how it's actually applied to blood flow. So I think you'll see that even though the the Navier Stokes stuff, hopefully you guys have seen that before. But we'll actually use that to draw some really interesting conclusions about blood flow. I think today's will be really interesting. Okay, and so the other announcement I want to make is that on Tuesday we're actually going to be back in the classroom. So the provost has emailed us and said that everything is good. So the infection rates are going down, and we should be good to return back to campus. And so starting Tuesday, I will be lecturing from the room. I don't remember exactly what room it is. I think it's one of the CS computer labs. I think it's CS 304, I want to say. And so you can come to the lectures there, and you can see me in person, live in the flesh. But just like I said at the beginning of class, I'm still going to continue on with the Zoom option. And so for those of you who don't feel comfortable coming to campus, or if you're working, I know a lot of you are grad students, you're working full time, then you're definitely welcome to keep attending the lectures on Zoom. And because it's all on Zoom, it's all going to be recorded as well. And so you're also welcome to watch the recordings afterwards. Okay. And so that's all the announcements I have to make. And so are there any questions I can answer before we get started? Yes, thank you. Okay, so yeah, CS 304. That's what I thought, but I haven't actually double checked all my classes just because we haven't had to come to campus. So Monday and Tuesday will be interesting as I try to find the rooms, probably same as you guys. Okay, all right, so let's go ahead and pick up where we left off. And so actually, let me go ahead and turn back a page, to where we were, just so I don't have to write down again. Okay. And so where we left off on Tuesday was we were interested in solving the Navier-Stokes equations and cylindrical coordinates to obtain the velocity distributions inside a rigid blood vessel, right? And so like we mentioned on Tuesday, the solution to this equation is credited to a couple of scientists, Hagen and Poiseuille, although most people credit to Poiseuille. Okay? And the Poiseuille solution, or the Poiseuille flow, is obtained by basically solving the cylindrical Navier-Stokes under rigid wall conditions. Okay, and so on Tuesday we started out with the conservation of mass equation, or the continuity equation, right? And so that's given by the boxed equation on the bottom of the page here. Okay, and you can see here that we've made some assumptions. And so we first of all assume that the radial velocity is 0, right? And so radial velocity here being UR. And we've also assumed that the polar velocity is also 0, and that's u theta. Okay, because remember we're basically just assuming that the flow is one-dimensional down the length of the tube. Okay, and so we only have, in other words, an axial component of the velocity. Right, and so by making those two assumptions, we go ahead and cross out the first two terms of this expression. Right, and so those two terms are 0. And we're only left with this term on the right here. Okay. What we get from this is that we have this equation that partial z is equal to 0. Right. And remember, what this tells us is that the axial velocity is assumed not to change at all as we're flowing down the vessel. Okay. And so in other words, what this conclusion is telling us is that we're having fully developed flow. Okay. And this is going to play a key role once we actually start getting into the momentum equation, which is going to be the next step. Okay. All right. So that was just a recap of Tuesday. And so hopefully that stuff is in your notes already. And now let's get started with the momentum part of Navier-Stokes. Okay. All right. So remember when we're talking about Navier-Stokes and conservation of momentum, there is actually three momentum equations, right? One for each direction that we could flow in. So there's a radial component of momentum, there is a polar coordinate component of momentum, and there's the axial one. But for our case, since we're only assuming that flow is going down the axial direction, or down the length of the tube, we're just going to go ahead and ignore the first two components. And so we're only going to write out the Navier-Stokes just for that axial component, okay? All right, and so with that said, buckle up because this is going to be a long equation, right? All right, so first we have the unsteady term, and so that's partial uz partial t. Then we have all the convective terms. Okay, and so all of those terms there belong to convection, okay? Next, we have the pressure term. Okay. Then we have gravity. Then we have all the viscous terms. Okay.
Dr. Trent, is that a negative one or p?
Yeah, it's a negative 1 over rho.
Oh, 1 over rho, sorry.
Mm-hmm. Yeah, remember I use P with the ponytail to indicate pressure, and then P without a ponytail is density, which is rho. All right. And so those are all the viscous terms. And so this is the conservation momentum equation in the axial direction. Okay. And so you can see it here. There's quite a few terms, and so there's a lot going on. And so we have basically all the craziness that we have in Cartesian Navier-Stokes, but there's kind of another layer of complexity here because we're in cylindrical coordinates. Okay. Okay. And so of course we're not going to solve this entire equation because that would be madness. It would also be impossible. And so, we're going to do what we usually do in these situations, in that we're going to apply some assumptions, right? And so, those assumptions are going to let us cross out a lot of terms of this expression. Okay. All right. And just so I could fit this all on one page, because I don't like to flip back and forth with these things, I'm going to color code this. Okay. And so I'm going to color code the assumptions that we're going to make, and then that's going to correlate to which terms it's going to allow us to cross out. Okay. All right, so the first assumption we have is the steady state assumption. Next, we have the incompressible assumption, although that actually doesn't do anything for us here, but I'm just going to list it out anyway. Okay. Next, we have the assumption of 1D z direction flow. Okay. Next, we have the assumption where we're going to ignore gravity. Okay. Next, we have the assumption of axisymmetric. Okay. And the last color here, this isn't really an assumption. This is kind of just a result of our continuity equation. We're going to assume that we have fully developed flow. Okay. I see there's a question in the chat. All right, question. So what's the difference between axisymmetric and radially symmetric? Yeah, it's a good question. So axisymmetric basically just means that things don't depend on the theta coordinate. And so axisymmetric is basically telling us that anytime that you see a derivative with respect to theta, that's going to be equal to 0, right? And so radially symmetric just means that because we have a kind of a circular geometry here, right? Radially symmetric just means that if you cross the radius like this, right, then everything on the north side here is going to be the same as on the south side. So it's basically symmetric across the radius, and so that's kind of what radially symmetric is. Yeah. Okay. Which in this case, we are going to get a radially symmetric solution just naturally, but it's it's not an assumption that we're making right off the bat. Okay, all right. So let's go ahead and start crossing out some terms because it's going to take a little while. And so let's start with the steady state assumption. And so remember, when we say something is steady state, then we say it doesn't depend on time. Okay. And so we look through our equation and then we cross out the term that has the time derivative, which is the very first term in our expression. Okay. Okay. For the incompressible assumption, we've already kind of applied that, and so we don't actually cross out any terms because of that. Okay. And so I'm going to go ahead and move on to the next assumption that we're making here, which is 1D flow. And so this is a big one. So this is actually going to get rid of a lot of terms for us. Okay. And so remember, our assumption of 1D flow basically is saying that the radial component of velocity is 0, so that's u sub r, and u sub theta is going to be 0 as well. So the polar velocity is going to be 0. And so anywhere we see u sub r or u sub theta in this expression, we're just going to go ahead and cross it out. Okay. And so you can see we have one right here, the first convection term, because we have u sub r there. We have one here, okay, because we have u theta. And so that's going to cross out, right? Oh, actually, that's it. That's the only two. I thought there were more than that. Okay. All right. So those are the terms we cross out with the assumption of 1D flow. Okay. Next, we have the assumption of gravity, right? And so we have one gravity term, and so we'll go ahead and just get rid of that. Okay. And that's the G term. And so I make it G sub Z because we're assuming that the pipe can go in kind of any direction that it wants. So the G sub Z here would just be the axial component of gravity if the pipe were slanted or something like that. But we don't have to worry about it too much because we're just ignoring it. But just in case you were wondering why I do G sub Z. Okay, next we have the axisymmetric assumption, and so any derivative with respect to theta, it can be 0. So we can see here that we have one on the convection term, and so that one is doubly gone. Okay. And we have another one right there in the viscous term, right? And so in the viscous term, we have a derivative there with respect to theta. In fact, it's a double derivative, and so we're going to assume that that term is also 0. Okay. And then finally, the last assumption that we're making, which again was the result of our continuity equation, is saying that our flow is fully developed. And so anywhere that you see partial uz, partial z in any form, we're going to set that equal to 0, right? So that's what the fully developed assumption is telling us. Right? And so you can see here we have one right there, and so we have partial uz, partial z, right? And we actually have another one at the end of the viscous term as well. Okay. And so both of those terms are going to go away with the same, using the same reasoning of, fully developed flow. Okay. All right. And so after doing all those cancellations, and so we've canceled out most of this equation, we're left with two primary terms. And so on the one hand, we have this term, which is our pressure gradient term. And then we also have this viscous term, which depends on the radius. Okay. And so those are the two terms we're going to work with, in solving for our velocity distribution. Okay. Any questions on this?
So is the left side equal to 0? Since
The left side is equal to 0, correct? Yeah, because we cross out everything on that side. Yeah. Mhm. Okay, all right. So let's go ahead and clean everything up. And so, with all those terms away, I'm going to go ahead and move. Actually, let me just write it out first. And so, after doing all those cancellations, we have 0 is equal to minus 1 over rho partial p partial z plus mu over rho, and so that's viscosity divided by density times 1 over r ddr of r duz dr. Okay. And one thing I did in this step was I changed all the partial derivatives into regular derivatives, because we only have one variable left, which is just the radius. Okay, and so we don't need to have partial derivatives anymore. Okay. Okay. All right. And so let me go ahead and clean this up a little bit more. And so you can see here that both the terms here have a density, which is kind of why I left it in that form. And so we can multiply both sides by the density and cancel that out. Okay. I'm going to take this pressure gradient term and move it over to the other side of the equation. And so what we get from this is partial p partial z is equal to mu divided by r times d dr of r duz dr. Okay. And now what our goal is, remember what we want in the end is we want uz, right? And so in order to obtain that from this expression, we're going to need to integrate this expression. Okay. All right. All right. So one thing that's going to help us out in this endeavor is we're going to make one more assumption. Although this one's actually really reasonable, and actually this holds even for most cases. We're going to assume that the pressure gradient here, dpdz, does not depend on r. Okay. Okay. And that's good because when we actually perform integrals here with respect to r, we can just treat it as a constant, and so we basically just don't have to worry about it at all. Okay. All right, so let's go ahead and start the process of integrating. And so I'm going to take this term, this mu over r, and move it to the to the left hand side by multiplying by its inverse. And so if we do that, we get r divided by mu partial p partial z is equal to d dr of r duz dr. Okay. And so let's go ahead and integrate this with respect to r. Okay. And so on the left hand side, we have a 1 over mu times partial p partial z, and so those are constants. And so, we don't have to worry about that, but we do have to integrate the r. And so we would integrate the r, we get r squared divided by 2 mu partial p partial z. Okay. And on the other side of the equation, we have, these two dRs are going to cancel out, and so we just get whatever's inside the differential, and so this is r duz dr, okay, plus we need to add an arbitrary constant to this expression, because these integrals that we performed, they were indefinite integrals. And remember, whenever we perform indefinite integrals, we have to add an arbitrary constant, because all indefinite integrals are only exact up to that arbitrary constant. Okay. All right. Next up, we're going to divide both sides by r. And then we're going to integrate again. Okay. And the reason we divide by r is so that we can kind of isolate this duz dr. Okay, and so we're going to divide both sides by r. Right, and so that's going to cancel out on that side, and that's going to have some effects on the other side. Okay. And I've run out of room, and so I'm going to go ahead and continue this this derivation on the next page. But before I get there, are there any questions on this?
You said assume dp over dz does not depend on r, but
Yes. Mm-hmm.
I'm a little confused because you only have partials like before and after. So I don't know if that's because I'm not understanding something or.
Yeah. No, it's a good question. So so this dpdz. What this represents is basically the pressure drop along the pipe. Right, because remember the z direction is the axial direction, so that points down the length of the pipe. And so what that dpdz, unfortunately I don't have a good image here. Let me go ahead and just draw one here, because I have open space. Right. And so remember, we're working on a system like this where it has flow in a pipe. And so all that dpdz is basically saying is that as we go in this direction in the pipe, our pressure should go down, right? Okay. The reason it's in derivative form is just to express the fact that it's not the pressure itself that we're concerned about here. It's the pressure gradient, and so it's the fact that pressure is changing down the length of the pipe. And in fact, it has to drop as it goes down that pipe. And so by making that assumption that it doesn't depend on r, what we're assuming is that if we move in this direction, in the r direction, right? And so say we go from the center line up to the wall. And we go from the wall to the center line, right? And so no matter what radial direction that we are, as long as we're still in the same axial location, right? And so we don't, in other words, we don't move down the pipe at all, the pressure gradient that we see is going to be the same, everything in that cross section.
Thank you.
Yep. Mm-hmm. Yeah, it's a good question though, because I think in all fluids class, and I do this too when I teach fluids, I think I just tell people that we'll just assume that this term is constant, but it's a little bit more nuanced than that. And I think it's important to know for this class in particular, because how pressure is kind of distributed in a cross section is an important concept that we'll actually come back to later when we talk about more biomechanics. I know I keep kind of saying that, but it's the thing with this class is that there's a lot of things that it's a lot of information that we're like, it'd be great to kind of stuff it all in at once, where it's like this thing affects that thing and this thing affects that thing. But class doesn't, and learning doesn't work like that. You kind of work, you kind of learn sequentially. And so I kind of have to just give you a little bit of a teaser right now, and then and then we'll come back to it later. Yeah. Okay. All right. And so we divide both sides by r. And if we do that, then what we get is we get we get an r 2 over mu partial p partial z plus c1 over r is equal to duz dr. Okay. And once again, we're going to be integrating this. with respect to r. Okay. On the right-hand side, all we get is, these dRs are going to cancel out, and we get uz of r. Okay, so that's great because that was our goal to begin with. And then on the other side of the equation, what we get is we get r squared over 4 mu partial p partial z. Okay. Next, we have the integral of c1 over r. And so that's going to be c1 natural logarithm of r, okay, plus c2. Okay. Right. And so now what we've arrived at here is the general solution for the velocity in a rigid pipe. Okay, but we're not satisfied with the general solution. And so we want to find a specific solution in this case. And so in order to get the specific solution, we have to apply boundary conditions to this guy. Okay. All right. And so we need two boundary conditions because we have two unknowns here. And so let me start with the with the central condition. Okay. Right. And so the first boundary condition that we're going to apply is that the derivative of the velocity with respect to r applied at the center of the pipe is going to be 0. Okay. And the reason we apply this assumption is to make sure that when we're at the middle of the pipe, we have a finite velocity. Okay. Okay. All right. And in fact, you can kind of see why we need this condition, even without actually mathematically applying it. Because look at this term right here. Okay. And so if we look at C1 times ln of r, right? And so if we plug in r is equal to 0, what's natural logarithm of 0? It's negative infinity, right? It's undefined. And so that's, that obviously can't happen. And so, everyone's not walking around in there with like black holes inside their blood vessels, right? That's not possible. And so in order for this velocity solution to be valid, this term just can't exist, okay? And the reason for that is because the center of the pipe is part of our domain, okay? But mathematically, if you want to see it, then, and the reason it takes this form is we're saying that, when we're in the middle of the pipe, and this is the velocity distribution. Okay. When we say the derivative is equal to 0, basically we're saying that we have a local maximum or a local minimum at the middle of the pipe. Okay. And so if we apply this mathematically, we can see that we have duz dr. Okay, and so I'm just going to take the derivative of that expression up there. And so we have r over 2 mu partial p partial z plus c1 over r. Okay. And this is equal to 0 when r is equal to 0. Okay. And so if we plug in 0 for r here, okay. And so that term just kind of goes away by itself. Okay. And we plug in, but if we plug in 0 for r on the c1 term, you can see that we have infinity. Okay. And so the only way for this to not be infinity is for that c1 term to just not exist. Okay. So we just need to Thanos snap it out of reality. And so, maybe if you've seen this in a previous class before, people have said that, C1 is 0, but that's not that satisfying to me because, we have basically 0 over 0, which is another mathematical black hole, right? So, the way I think about it is that, if you have, if the center of the pipe is inside your domain, then that term just can't exist. And so we just get rid of it. Okay. All right, any questions on that? Okay. All right, so that's the first boundary condition. And so now that we've gotten rid of that C1 term, that only leaves C2, okay? And so to solve for C2, we're going to apply the condition where we have no slip at the walls. Okay. And I'm going to use the symbol big R here to denote what the radius of the pipe is, okay? Okay. And so if we take our velocity solution here, okay, and then we plug in big R. Okay, so actually we're gonna apply this at u of uz of big R. Okay, then we have big R squared divided by 4z partial p partial z. Okay, plus C2 is equal to 0. Okay. And so all we have to do is we just have to move this guy over to the other side of the equation. Okay. And then we get C2 is equal to minus R squared divided by 4 mu. Sorry, this is 4 mu. I don't know why I have a z there. Sorry, that should be divided by 4 times mu, which is the viscosity. Okay. Minus R squared over 4 mu times partial p partial z. Okay. And then we plug that back into our velocity solution. And then we finally get our full velocity profile. Okay. And so there is our final answer for the velocity profile inside a rigid blood vessel. Okay. And this is what's known as the famous Poiseuille solution or Poiseuille flow. All right. And so let's take some observations. So let's take a step back and look at this flow and see what it kind of looks like. And so the key parameter here I want you to look at is the fact that we have, actually let me circle this whole term, is the fact that we have R squared. Okay. And so what kind of function is like an x squared or an R squared function? This is a parabolic function, right? And so if you plot this, and we'll kind of neglect a lot of the constants for now, okay? And so if you plot this as a function of R, okay? And so let's say that this is an R axis, right? And so you can assume that the cross section of the pipe is something like this, okay? Then what the Poiseuille solution tells us is that the velocity profile here is parabolic, okay? And so it looks something like that. Where here, this is uz of R, okay? All right. And so that's kind of the reason why when people talk about Poiseuille flow, outside of the classroom, sometimes people just call it parabolic flow. And so parabolic flow, Poiseuille flow, they all mean the same thing because the Poiseuille solution has a parabolic character to it. Okay. In other words, the velocity solution depends on R squared. Okay. All right. Any questions on this? Okay. All right. So now that we have the Poiseuille solution, let's use it for some stuff. Okay. So the first thing I want to do is I want to take this Poiseuille solution and I want to integrate it across the cross-sectional area. Okay. And the reason I want to do this is I want to compute volumetric flow rate. And the way that you can compute flow rate from any velocity distribution is integrated with respect to area. Okay. All right, and so the flow rate is going to be given by the symbol Q. Okay, and so Q here is going to be the integral with respect to area of uz of r dA. Okay. But since we're in polar coordinates here, we can substitute an expression for dA. Okay, and so dA is going to be 2 pi r dr for cylindrical coordinates. Okay, and because we're doing that change of variables instead of dA to dr, we can change our integration bounds as well. Okay, and so our integration bounds are now going to go from 0 to big R. Okay, so we have a definite integral this time. Okay. And so we're going to take the integral of uz of r times 2 pi r dr. Okay, and we're going to integrate that from 0 to big R. Okay, and so we're going to take our velocity solution, which is what we got on the previous page, and just plug that into the integral, and then perform that integration. Okay. All right. So just because I kind of want to get to some of the newer stuff, I'll let you guys verify this yourself. But if you perform that integration, what you get is minus pi big R to the 4, okay, divided by 8 times mu times partial p partial z. Okay, and that's what the flow rate is. Okay. All right. Okay. I'm going to go ahead and do one more thing with this expression, just because it's going to set us up for something we're going to do later. I'm going to go ahead and plug in for the pressure gradient here. Okay, because what I want to get is a relationship between pressure drop in a cylinder versus the flow. Okay. And so we're going to make a literal substitution for the pressure gradient in this expression. Okay. And so instead of the derivative partial p partial z, we're going to replace it with a change in pressure, or delta p, divided by length, which is the length of the pipe. Okay. And so visually, what I'm doing here is I'm saying that if we have a pipe like this, okay, and the length of the pipe is L, okay, that along that length, our pressure is going to drop from P1 to P2. And so delta P here is going to be P1 minus P2. Okay. All right. And so if we plug that in, then what we get is Q is equal to minus pi r to the 4th over 8 mu times delta P over L. Okay. And so if we move kind of everything to the left-hand side except for delta P, then we get the following relationship. And so what we get is delta P, or the change in pressure in a segment of cylindrical tubing, okay, is equal to a pi L divided by pi r to the 4th times the flow rate. Okay. And this equation right here is relationship between pressure drop and flow rate. Okay. Relationship between pressure drop and flow rate in a cylindrical pipe. Okay. All right. Any questions on this? Question in the chat. Yeah, 8 pi L, correct. Yeah, 8 times pi times L. Oh, 8 mu. Sorry, I'm sorry. Yes, yes, you're right. Right. So it'd be 8. It'd be 8 times pi, 8 times mu times L. Yeah. Thanks for catching that. Okay. Okay. All right. And so now that we have the Poiseuille solution and we have this relationship between pressure drop and flow, let's actually apply this to some blood vessels, and let's come up with some interesting physical laws that blood vessels actually actually do a good job following. Okay. And so the first law that we're going to go over for blood vessels is known as Murray's law. And Murray's law is very fascinating, but and you can actually derive its or explain its mechanisms just purely based on rigid fluid mechanics, which is kind of what we did right now. But it explains a lot of how of how vessels are sized within your cardiovascular system. Okay. All right, so first, let's start with the definition. And so I want to define a term called bifurcation. All right. And so what is a bifurcation? And so a bifurcation is basically just whenever a blood vessel splits into at least two more daughter vessels. Okay. Okay. All right. Because the reality of your cardiovascular system is that your body needs blood to go to a lot of different places in your body, right? And so it needs to go to all the muscles, all your organs, your brain, and all that stuff. And if you had just a single pipe of blood, a blood vessel that goes through your entire body, that would be extremely inefficient because your blood would have to travel in that one pipe to all the parts of your body. It would be kind of the same thing if we only had a single freeway in Southern California, right? And so if everyone had to get on that freeway to go from Fullerton to Long Beach to LA to San Diego, right? It would be awful, right? And so you wouldn't be able to get anywhere because it's just one road, and there's just a lot of places that people need to go, and that wouldn't work. Okay. And so in order for your cardiovascular system to work efficiently, it needs to split, right? And so it needs to split it up into multiple multiple blood vessels. And so visually it looks something like this. Okay? So you have a blood vessel coming in, okay? And so this would be the parent vessel, right? Okay. And then it would split, in this case, I'm just going to do a 2 split, okay? It would split into 2 daughter vessels right here, okay? All right, and so let's say that the radius of the parent vessel, we'll call it RP. Okay. And for the first daughter vessel, we'll say it has a radius of RD1. And the second daughter vessel has a radius of RD2, okay? We'll call this vessel 2, vessel 3, okay? All right, and so the way that we kind of describe this with words is we say that vessel 1 is bifurcating or bifurcates into vessels 2 and 3, okay? All right, what's interesting about this scenario here is that, even though I kind of drew them arbitrarily, there's actually a relationship between the radius of the parent vessel and the radius of the daughter vessels, okay? Okay. And so, when you first read this, and even, when you're kind of naively kind of drawing blood vessels that bifurcate like that, I think everyone kind of sees that, yeah, probably the daughter vessel will have about the same size as the parent vessel, maybe a little bit, maybe it'll be a little bit smaller, because they're splitting off from one vessel. Maybe each of them are about half the size as the parent vessel, right? And so, I think we kind of have some of that intuition, but there actually is a mathematical expression for for how these radii are related, and you can actually derive that reason just purely based on fluid mechanics. Okay, so purely based on what we've discovered, you can find this relationship, and the even more fascinating thing is that your body just naturally, just by itself, has also picked up on this relationship as well. But as we'll see, as we go through the proof, that it's actually a very ingenious kind of relationship, and even more fascinating that the body kind of picked up on it on its own. Okay. So any questions on this before we jump into that proof? Okay. All right. And so the main motivating factor for why there's an optimal relationship between RP and RD here is the fact that your body wants to minimize power consumption. Okay. Because in order to push your blood through the entire body, it takes some energy from your body, right? So your heart is your heart's never stopping, right? And so it's always pumping. And so ideally, when you have a system like that, you want it to work as efficiently as possible. And so it would be great if when things happen in your cardiovascular system, like the blood vessel has to bifurcate, that it does so in the most energy efficient way possible. Okay. I should say body wants to optimize power consumption. Okay. And so throughout the process of evolution, or or however you believe our human bodies came to be, at some point your body was like, can we design this system in a way such that the heart doesn't have to work so hard to push blood through. And in fact, there was. Okay. And so let's talk about some of the factors that affect the amount of power that your heart has to output. Okay. And we can explain those and motivate these reasons just purely based on fluid mechanics. Okay. Okay. And in fact, there's two main factors. Okay. Okay. And the fascinating thing is that both of these are based on the radius. Okay. And so they depend very strongly on the radius of the vessel. Okay. And these factors are actually competing with each other as well. And so, as one factor, becomes more dealt with, the other factor actually becomes more of an issue, which is even more fascinating. Okay. All right. All right. So let's talk about what happens when the vessel radius decreases. Okay. And so as the vessel radius decreases, okay, this is going to increase the power that your body has to output. Okay, because it has to overcome viscous forces. Okay. Okay. Right, and so as your vessels get tinier and tinier, you know, the amount of viscous shear or viscous forces is going to increase. Okay, and intuitively you can kind of think of this as, you know, think about if you're trying to squeeze a bunch of fluid into a tiny, you know, into a tiny tube, right, into a tiny, you know, straw or something like that, right? And so it takes a lot of work. And so as the straw gets smaller, you know, if you want to squeeze more and more fluid through there, it's going to take a lot more. It's going to take a lot more work, right? And so think of you know, if you're a fan of boba, right? So if you think about trying to you know, sip up your milk tea with like a big ass boba straw, right? So that's pretty easy, right? Because the straw is huge. But try to think of sucking up the same boba with like a really tiny coffee stirrer straw, and that's a lot harder, right? Because it's a lot smaller of a space. Right? I didn't find out until like I was in college that those tiny coffee straws were not actually straws; they're just for stirring. And so, you know, I was drinking, trying to drink stuff up the wrong way for a large portion of my life. Okay. All right, and so, you know, with that in mind, you would think that, you know, increasing the radius, you know, that's going to decrease the amount of power that your heart has to put out, right? But there's actually another effect that happens when you increase the radius. Okay, and so when you increase the radius, the blood volume also increases, which is just the sheer volume of blood that's inside your body. Okay. Okay. And if the blood volume increases, then the amount of mass that your heart has to push around is also going to increase. Okay. And so just by that nature of, you know, having more blood in your body with bigger vessels, this is also going to increase the amount of power that your heart has to consume. Okay. I believe on Tuesday we talked briefly about the concept of inertia, right? And so the more mass that you have, the more inertia it's going to be, right? And so pushing around a small Hot Wheels car is a lot easier than trying to push around your, you know, your normal car that you drive, right? Just because the normal car has just a lot more inertia, okay? And so these two, you know, both of these effects are, you know, they're both true, right? And so if you decrease the radius or increase the radius, you know, it's going to lower one lever but increase the other one. And so these two factors are competing with each other. And usually, you know, when you have competing factors, you know, in physics like this, that implies that there's some kind of Goldilocks spot. And so there's basically some kind of optimal radius that kind of does the perfect balance of these two. Okay. Okay. And so what we're going to do is we're going to come up with what that perfect radius is, you know, by basically coming up with mathematical expressions for both of these factors and then balancing them against each other. Okay. All right, any questions on this? All right, question. So do these two factors relate back to high blood pressure, or is this only dictated by the capillaries? Yeah, it actually does. And so, you know, the main thing that causes high blood pressure is actually the first factor right here. And so this first factor actually has this one has a much stronger effect on pressure. And so, you know, and that actually directly relates to your capillaries too. And so as your capillaries get kind of smaller and stiffer, which is kind of what happens when people get older, then it requires much more pressure to actually push through them. And so people with high blood pressure, a lot of the times they have, you know, really tiny or really stiff capillaries. Yeah, and that's mostly just due to that first factor there.
And low blood pressure would be if the person have the veins that are too thick?
Low blood pressure is a little bit different cause. So low blood pressure is more due to like a weakened heart. Yep. And so if you have a nice big healthy capillaries, then your body still will kind of maintain a healthy blood pressure as long as your heart is strong enough to. And so low blood pressure means your heart's just not there. Yeah. Okay. All right, so let's come up with some mathematical expressions for both of these guys so that we can actually balance them. Okay. And so throughout all this, let's come up with a kind of a characteristic case. Okay, so let's assume that we have a single blood vessel. Okay. And so let's say that this blood vessel has a radius of big R and a length of L. Okay. All right. And so under these conditions, let's characterize, or let's come up with a formula to characterize the amount of work that the heart has to perform to overcome those two factors. Okay, and so let's start with the viscous factor. Okay. Okay. All right, and so actually going off Kevin's question about high blood pressure, right? And so generally speaking, the thing that overcomes the viscous force or the viscous shear force is a higher pressure, right? And so in order to squeeze through blood into a blood vessel to overcome the viscous forces, the primary way that the blood does this is through pressure. Okay. Okay. All right, and so let's go ahead and characterize that. And so the pressure force, I'm going to call it FP. Okay. This is going to be simply equal to the difference in pressure. Okay. And so we're going to assume that we have a pressure drop from P1 to P2. Okay. And so this is going to be simply equal to delta P times A, right? Because remember, pressure is just a force divided by an area. And so if we multiply pressure by area, that's going to give us a force. Okay. Okay. Right. So now that we have an expression for the amount of force that the pressure has to exert, we can obtain power by multiplying this by the velocity. Okay. Okay. Right, because that's one of the definitions of power, right? So one of the definitions of power is force times velocity, right? And so power, okay, and I'm going to denote power as W with the dot on top, okay? And so remember, power is also the time rate of change of energy, right? Or time rate of change of work, okay? And so power here is going to be FP multiplied by velocity, okay? And the velocity that we're going to multiply by, and we'll keep it simple here. And so, normally you would multiply it by the velocity distribution that we derived earlier with the Poiseuille flow. But just to keep things simple here, I'm just going to multiply by the mean velocity. Okay. The mean velocity being kind of like the average velocity across the cross section of a blood vessel wall. Okay. And so let's go ahead and plug in for FP. Okay. And so FP here is delta P times A. Okay. And so that's going to be multiplied by A times U, U bar. Okay. But here we have the product of the cross-sectional area multiplied by the mean velocity. Okay. And so it turns out that this is actually another definition for Q, which is our volumetric flow rate. Okay. And so if we plug that in, then we see that one expression for, or one model for the amount of power that the pressure has to exert is delta P times Q. Okay. All right. And so what I'm going to do on the next page is that, remember, we derived that expression or the relationship between delta P and Q in a rigid blood vessel. And so I'm going to go ahead and plug in for Q for that. Or excuse me, I'm going to plug in for delta P. Okay. Okay. And remember, that was an expression that we, that we derived earlier. The one where I mistook mu for pi. Okay. All right, any questions on this? Okay. All right. And so if we plug in for delta P, what we get is W dot visc. Okay, this is equal to 8 times mu times L divided by pi r to the 4th times Q. Okay, and that's multiplied by Q. Okay, and then we multiply the Q together, and what we get is 8 mu L divided by pi r to the 4th times Q squared. Okay. All right. So this is great right here because we were able to kind of work on this expression until the radius popped out, right? And ultimately, that's what we're trying to determine here is, what's the relationship between the radii of the parent and the daughter vessels. And so the fact that we popped radius out of here is a good thing. Okay. Okay. And so that's an expression for basically how much power the heart has to output to overcome viscous forces. Okay. All right. So now let's come up with a similar expression for inertia. Okay. And so the amount of power that the blood or that the heart has to output to overcome the blood volume's inertia. And so we're going to be a little bit more hand wavy on this one, just because we don't have to be too precise here. And so what we're basically going to assume, and it's a very reasonable assumption, is that the amount of inertia work or inertia power that the heart has to output is going to be directly proportional to the volume of blood. Okay. Okay. And so what we can say here is that W dot inertia is equal to B times the volume. Okay. Where little b here is just some kind of proportionality constant. Okay. And so, that's basically what we're assuming. It doesn't really matter what that constant is because you'll see that we'll kind of get rid of it later. But if we plug in for the volume, then what we get is, and remember, we're just looking at just that one blood vessel segment. And so this will be pi times the radius squared times the length. Okay. Okay. And so the total amount of power that the heart has to output is going to be the sum of these two things together. Okay. Right. So W dot total is going to be 8 mu times L divided by pi r to the 4th times Q squared plus B times pi r squared L. Okay. All right. And so that's an expression for the approximate total amount of power that the heart has to output. Okay, but remember, we're interested in minimizing this quantity because the heart wants to be as energy efficient as possible. Okay, and so let's take this expression and let's take the derivative of it with respect to r. And then we're going to take that and set it equal to 0. Right, because that's going to allow us to solve for a minimum of this function. Okay. All right, so I'll go ahead and do that on the next page. But before I do that, are there any questions on this? Okay. Okay, and so if we do that, and so we take dw dot dr, what we get is minus 32 mu L divided by pi r to the 5th times q squared plus 2b pi rl. Okay, and then I'm going to set this equal to 0 and solve for r. Okay, and so I'm going to go ahead and move this term over to the other side of the equation because it has a negative on it. And so we get 32 mu L divided by pi r to the 5th q squared is equal to 2b times pi rl. Okay. And so we can see here that the L's are going to cancel out, and so we don't have to worry about those. Okay. The 2 here is going to change this to a 16. Okay. I think that's everything that we can cancel out. Right? And so just to get all the r's on one side of the equation, I'm going to take this r to the 5th and multiply it over there. Okay. And what we get after performing those, we get 16 mu q squared divided by pi squared b. Okay, this is equal to r to the 6th. Okay. And then from this, what we get is 16 mu q squared divided by pi squared b, all raised to the 1/6 power. Okay. Okay. All right. And so, and so this is great, right? And so we have a radius here, but it's actually not 100% helpful to us because, even though a lot of these things we can compute, we still have this guy left right here. Okay. And so B, and it was partially our fault because, we're partially lazy because we didn't want to compute the amount of inertia power. Okay. And so right now this formula isn't super helpful to us. Okay. But at least we know that by performing this derivation that there is an optimal radius, and so there is one that exists. Okay, and so even though we weren't able to get an exact solution, we were able to get a solution, which is not a bad thing. Okay, and so I'm going to do this, and so I'm actually going to work off this expression right here. Okay, and then I'm actually going to solve this for q. Okay. All right, and so if we move everything that multiplies by q to the other side of the equation, what we get is q squared is equal to pi squared b divided by 16 mu times r to the 6th. Okay, we take the square root of this, we get q is equal to square root of pi squared times b divided by 16 mu r cubed. Okay. And so I know it seems like we're going around in circles, but I promise you we're almost done. And you know, I've been trying to time it so that we get to this kind of nice moment right at the end of class. Okay. But yeah, this proof does it's not the proof I'm most proud of, but the result is really cool. Okay. Okay. And so before I move on, just so I can save a little bit of time, you know, I'm going to go ahead and circle this term right here, right? And so this term consists of pi's. It consists of b, remember, which is just a constant, divided by 16. 16 is also a constant, and as well as mu, which is the viscosity. Okay, so this entire term here under the radical, this is a constant term. And so we're going to replace this with another constant. Okay, and so we're going full exhibit here. You know, constants on constants on constants, and so. You know, I'm just to kind of save writing here, I'm just going to substitute this with k. Okay. Okay, and so if we plug that in, we can see here that we have q is equal to k times r cubed. Okay. Right. So this by itself is q stands for volumetric flow rate. Yeah. So q is basically like meters cubed per second or milliliters per second. Yeah. Mm-hmm. So this result here is actually interesting on its own. And so, you know, what this is saying is that the amount of flow or the amount of volumetric flow rate that's passing through a vessel is actually proportional to the radius cubed, you know, which is actually pretty interesting. Okay. But this is actually really useful because we can take this and we can finally bring it back to our bifurcation, right? Because that's kind of where we started, and that's kind of what we want to learn information about. Okay. So before I bring it to that, are there any questions on this part here?
Really run out of all the English letter and went back to K.
Yeah. We've used a lot of them, but we haven't used all the Greek ones, and so you know, we have all of those to go. Even COVID hasn't gone through all the Greek letters yet. Although, you know, knock on wood, let's hope we don't go through that. Okay, all right. So let's go ahead and bring this back to our bifurcation. Okay, and so remember, you know, we started off with a situation like this, right? And so we have a vessel that splits off into two. And so we have a parent vessel 1, and we have each of the daughter vessels 2 and 3. Okay. All right. And so, you know, the reason I kind of went through that entire, you know, derivation to get, you know, that relationship between flow and radius, because that's kind of exactly where I want. Okay. Because right now, you know, remember, we're trying to find out what the relationship between, you know, this radius, and this radius is, right? And so we want to find that relationship. But one thing that we do know for sure is that mass is going to be conserved in this bifurcation. Okay. And so that any flow that you have coming in, and so let's say that we have a flow of Q1 coming in, okay? This has to equal the amount of flow coming out, okay? Okay. And so the mass has to be conserved, and that has to be true no matter what. Otherwise, the universe as we know it would implode, okay? All right. And so let's take this expression and let's substitute for Q according to the relationship we had on the previous page, okay? And so Q1 here we know is equal to K1 times the radius 1 cubed, okay? Q2 here has to be K times the radius at 2 cubed, okay? And Q3 is equal to K times the radius 3 cubed, okay? And all of these Ks are exactly the same, okay? And so if all these Ks are the same, then we can cancel out, right? Right? And we can do that, remember, because if we look at the expression for K, none of that depended on the vessel itself, right? So none of it depended on the size of the vessel or the length of the vessel at all, right? So we can do this, okay? And so because we can cancel those Ks, we finally arrive at Murray's law, okay? And so Murray's law basically says that in order for, you know, whenever you have a bifurcation of a vessel, in order for it to be as power conserving as possible, then the parent and the daughter vessels have to follow these rules. Okay, so if you take the radius of the parent vessel, you raise it to the third power, this has to be equal to the sum of the radii of the daughter vessels also raised to the third power. Okay, right, so this here is Murray's law. And so Murray's law is something that the body has determined on its own. And so if you actually measure the blood vessels in the body, and this is true to varying degrees, but to varying degrees, the blood vessels actually follow this law pretty well. Okay, and it's something that we derive just purely based on fluid mechanics. Right, and so that's the conclusion for today, right? And so are there any questions on this before we wrap it up for the week? Okay, all right, so that's all we got time for. So I know I ran over time a little bit, so I appreciate you guys staying a little bit extra. So thank you guys for tuning in this week. The lecture recording should be up later tonight. Remember, next week we're back in the classroom, and so I will see, if you're coming to campus, I will see you then. But regardless, I hope everyone has a great weekend.
I have a question.
Yeah.
It's regarding the homework.
Yeah.
For the medical devices, do you want that 2-page in a certain format or like?
No, just 2-page typed up.
Okay.
If you can make it single spaced, that would help.
All right. Sounds good.
Yeah.
All right. Thank you.
Yeah. All right. Question. So the negative sign change from the delta P on page 18, because I didn't see the negative sign. Okay, let's look at page 18. This one right here, or the next page? Maybe it's the next page, or the previous page, or page before. Oh yeah, sorry. Yeah, so the negative sign, I crossed that out with the delta P. Yeah, so I did it. I did that reversed. Yeah, so I kind of because the delta P is a difference in pressure between upstream and downstream. I just kind of lumped the negative sign into there. Yeah.
Dr. Trent, quick question on the equation we have at the end. So does that also governs how so the blood vessel split, and then eventually have a limit, it can't split anymore. Does that equation also indicate how small it can split, or?
Not really, and so that's kind of more limited to at least when you're talking about the human body, that's more governed by how big the blood cells are, and so the ultimate size of the capillaries can't be smaller than a blood cell, because if it was, then there's nothing that can go through it. So this just relates to what's the most power efficient way to split if you have one pipe going to another pipe. But the interesting thing is, like, this also it's not just blood that this governs, and so this can also apply if you're designing like a piping system, and it has to split off into two. You can relate kind of the inlet and the outlet vessels, or inlet and outlet pipes, along with this, and that's going to be the most energy efficient thing to do. Yeah.
Interesting. Thank you.
Yep. All right. Question. So is the medical device research single space, double space? I would prefer single space, just because I think it's a lot of information, and so I think single space would help you kind of get in all the information there. But remember, you can also include figures in there as well. But yeah, I do prefer single space.
Thank you, Dr. Trent.
Yep.
Thank you.
Yep. Have a good weekend, guys.
Thank you.
Preston, did you have any other questions? Okay. All right, so I'm gonna go ahead and sign off. So I'll see you next week.